Continue where I left off on Thursday, but let me just remind you with a few slides what we talk about so we can get back into the mood. The IO model, we look at problems containing n elements. We have a processor, main memory, and a disk. The main memory holds m elements, and we move stuff between the disk and main memory in blocks of size b, and that's the only thing we count. We count how many of these block IOs we're doing. Then I showed you this slide that basically showed you the important bounds in the IO model. So we're used to linear being n. It's now n over b because we can read b elements in one IO. So to read all our input is n over b IOs. Sorting, we're used to n log n. It's also n log n, sort of, if we measure things in block. And remember that the base of the logarithm is now the number of blocks in memory instead of 2. Permuting was then the interesting thing. So if we want to just move n elements around according to some permutation, if we just do it one element at a time, you're going to spend n IO, but actually in most cases we can do much better by sorting. And as I said, this b here in the denominator here is very, very important because b is very, very big. So going from an algorithm that uses n to one using n over b algorithms, n over b IOs is very important in practice. Just to remind you, sorting is this thing where we start by creating sorted runs, so memory loads of sorted elements, and then we start merging them together m over b at a time. And this was this key thing about the IO model, that we can merge m over b things together in linear IO, where we're used to doing 2. Since we in each level can use, of this merge tree, can use linear IOs, we get the optimal sorting algorithm. And then I talked a little bit about distribution sorting, which was just turning this thing upside down. Then we went and did the permuting lower bound. Remember, that was a counting argument where we computed or estimated how many permutations we can produce with TIOs, and then we compared that to n factorial, and then we got the permuting lower bound in the indivisibility model. So this model of computation where we could only move elements around. We're not allowed to break up elements or make new elements. We can only move them around. But then I mentioned to you that you can also do a sorting bound where you assume not the indivisibility model, but instead the sorting, the comparison model in internal memory. So the only thing we can do with elements are comparing them. And there you can do, I just told you, you can do the same kind of argument where you lose this term and therefore you get a slightly different bound. Then I talked about cache oblivious algorithms shortly. So cache oblivious algorithms was these algorithms where we also work in the IO model with the same parameters, except that we're not allowed to use m and b in our algorithm. So therefore we have to assume that somebody else is doing the IOs for us. So we assume that it's an optimal paging strategy that does it. Then when we analyze algorithms in the IO model with m and b, if we analyze an algorithm and see that it's efficient or even optimal, then it actually is automatically optimal on all levels of the hierarchy, of any hierarchy, since we didn't use m and b. So we didn't tune it to some particular hierarchy, and therefore it's optimal on all levels. Then I showed you this somewhat funny sorting algorithm. Let me just give you the idea. So the idea is like doing distribution, instead of doing m over b way distributions, which we can't do anymore because we can't use m and b, we do square root n distribution. But to do that efficiently, we start by breaking our data up into root n subarrays of size root m, sorting them recursively, and then we did this weird distribution where we did sort of a recursive 4-way thing, and I argued that that took me n over b IOs, which meant that I got this recursion that solves to the sorting bound. The whole trick here was to do recursion root n-wise such that the problem automatically comes down and fits in memory at the right time. So this was sort of all I talked about in sorting: merge sort, distribution sort, and cache oblivious sorting. And they're all these sorting algorithms that has large merging or distribution. They are optimal in the comparison model, and I also showed you this permuting bound. Then the last thing I did was distribution sweeping, which I'm sure you're intimately familiar with now. So this idea of when you want to solve a batch geometric problem, so you have some objects in the plane, you break them up like its distribution in M over B slabs with roughly n divided by M over B points in each. You do some sweep to get the individual slabs to be independent, and then you recurse. That has been that kind of idea has been used to solve a lot of problems, and hopefully you managed to solve yet another one. Yes. So that was in I guess 2 minutes what I did on Thursday. So here's what I'm going to do today. I'm going to continue and talk about going from sorting to searching, doing B trees, batch searching buffer trees, talk about priority queues, and then show you how actually to use this priority queue on a particular problem, namely the one that I talked about way in the beginning, namely the simplest graph problems, if you like, you can think of, namely list ranking. All right, so judging from last Thursday, I suspect that a whole bunch of you know the first part that I'm going to talk about now, namely B trees, but I'm going to do it anyway just to warm up for the next stuff I'm going to do. And again, remember to to ask questions, right? You realized last time that I make mistakes, right? So point them out and we'll fix them online here, all right? And also if there's stuff you don't get, then ask me and I'll try to explain it again. All right, so external searching. So we're used to, when we want to search, we build binary balanced search trees, right? So we build these trees here of height log n. In everything I say from now on, my data is going to be in the leaves, okay? So here I have n elements sitting down here in sorted order, and I build a search tree on top of them. The search tree, the stuff that are in the nodes here are just things that guide my search. My real data is down here. Okay? When I want to find an element, I of course just search down the one path using log n time. And similarly, if I want to do a range search, so find stuff in a range, then I can search down and walk along the leaves, or I can search down two paths and walk along the leaves, right? If I just put this tree on external memory, so ignoring that it's big, that it can't fit in memory, then you can quickly realize that a search is going to take you log base 2 of n IOs, right? Because I'm going to go out on a disk getting this node, and if I'm not careful, the other stuff that I'm going to get from disk is way some other places in the tree. So every time I take a step here, I'm going to spend an IO, right? Similarly, every time I take a step down here in the leaves, I'm going to spend an IO. So performing a range search is going to be log n plus t, which is not what I want, obviously. I want to make good use of my IOs, right? When I get one node, I want to make sure that I get some other nodes that I can use. So the natural thing to do, which is actually what we're going to do, is we're going to just block our tree, or think about blocking our tree breadth first search, right? So I'm going to start up here, I'm going to take the root, its two children, their children, and so on, until I've collected B nodes. I'm going to put them in one block. That small tree that I have sitting in here is going to be of height log 2b, log base 2 of b, right? Okay, B nodes in here, and then I'm going to continue doing this recursively, and I'm also going to stick B elements in each leaf. And then it's actually quite easy to see that if you do a search down one path, how many IOs are you going to use? Well, you're going to do an IO to load this node, right? But then you're going to get these two here for free. And only when you go to this block, you're going to have to load this next block. So you get this path for free. This path is of height log b, right? So to go down one path of height log n, you spend log n divided by log b IOs, which is exactly log base b of n, which is the bound that I would like. Similarly, when I go along the leaves here to do a range search, I'm also on the average going to get b elements every time I do an IO, because there's on the order b elements in a leaf. Okay? So that makes sense? So just being stupid and just blocking the tree breadth first search makes you actually get these nice range searching, these bounds here, which you can easily prove are optimal, right? This is stored in a linear number of blocks, so it's linear space. The log base b of n bound is optimal, which you can prove just like you prove that log base 2 of n is normally optimal. And t over b is exactly the number of IOs I need to report t elements, right? So I can't do any better there either. So the search is optimal and the output is optimal. Yeah. So these are just, guiding elements, right? When up here in the root, I have an element that's sort of the middle between these two guys here. A little bit, but I don't really care. But what I'm going to show you in a minute is how to actually do this dynamically, and then it's going to show you how to build the tree. Good. Other questions while we're at it? Okay? So that's just taking a binary tree, blocking it, and we have an external memory tree that behaves like we want it to behave. Let me just, before I do dynamic, I want to just go and talk cache oblivious just for 2 slides because it's cute and easy. So remember, cache oblivious is the same as IO, except I'm not allowed to use M and B. So particularly, I'm not allowed to use B. And what did I do here? Here I took my binary tree and I blocked it in a way that's highly dependent on B, right? I said put the top B nodes in this block and recurse. I cannot do that when I'm not allowed to use B, right? So what do I do in the cache oblivious model? Well, I use this thing we usually refer to as the Venom de Boer's recursive layout. So here's my binary tree from before. So it's a tree like this. It's of height log n. What I'm going to do is that I'm going to cut it at the middle. So I get, conceptually, so I have a tree up here of height half log n, and I have a bunch of trees down here of height half log n. Okay? Then I'm going to take this tree up here and I'm going to put it out here in memory. This guy I'm going to put after it, and so on, recursively. Okay? So this tree is going to be put out in memory here. I'm going to do it like, I'm going to take the top part of it and I'm going to put it here, and this tree I'm going to recursively put here, meaning on the next level I'm also going to cut that in half and put pieces in here. So all this does is it tells me for each node over here, where does it go in memory. Okay, so I've just taken this tree and linearized it. I put it out in memory in a particular order, and the order is defined recursively like this. Make sense? Okay. Why is that good? Well, imagine that we do a search down one path. Let's see how many IOs we do. We can analyze it by looking at the way I recursively assigned the nodes to memory. So this was the first level of recursion, right? This tree was put together and these were put together. The next level recursion, these were put together and so on. Look at the level right where these small trees becomes of height log B, or between half log B and log B, right? When they have between root B and B elements in them, right? So I go down the recursion, I think about how does the tree look at this point. This is only for analysis, not for the algorithm. If you think about it, then all these nodes here, they're going to be lying together in memory somewhere, right? Because the recursion would put them together. These are going to be somewhere in memory. These are going to be somewhere in memory. These are going to be somewhere in memory. That means that when I go and load this node here, I'm actually going to get all these for free. The optimal paging strategy is going to give them to me. They're right next to. So I can walk through this tree without I/O. When I land here, I'm going to load, access an element here. I'm going to get all the other ones too. So I can walk through this guy in without doing I/O. And I can do the exact same math as I did before to walk a path of height log. There should be a 2. To walk a path of log n height, I do log n divided log b IOs, namely log base b of n IOs. Okay? So instead of explicitly putting these things out in blocks, I do it recursively like this, but the effect is going to be exactly the same. Namely, at some level, the blocks are going to be exactly the right size. Pretty neat, I think. All right, but let's forget cache oblivious and go back to this picture again. What if I want to maintain this recursively? Well, normally when we maintain balanced search tree, we do it with rotation, right? Right? Right. So a rotation is this process of, if I have this tree, if I rotate around x, it's like taking x and pulling up, right? So x comes up here, y falls down, and the trees fall like they have to. That's a rotation. That way, right? That way. What happens to my blocking when I do this rotation? Well, I try to indicate it here. Let's say this guy is the last node in a big block. This x here is the first node in this block. This is the first node in this block, and so on. When I do the rotation, what happens is that things are going to sit like this, right? X is sitting here. It had some small part of this tree. It had some part of this tree. The blue guy here sitting here has nicely over here. But y has suddenly fallen down here. It was up in the block. So it's sitting together with some other stuff up here. This y needs to go in this block, right? That means that there's not room for all this red stuff. And it's also unbalanced now. So I need to redistribute this red stuff, taking some of these, which means that it cascades down the tree. Basically, it doesn't work, right? When I do this rotation, stuff gets messed up, which means that I need to move all kinds of stuff around all the way down underneath the node. That's going to take me way too many items. Okay? So I'm basically saying I cannot maintain this blocking during rotation. So on one hand, it was nice. I went from binary to external memory just by blocking the tree. On the other hand, it's bad because I can't maintain it when I do rotations. All right, so instead I do something else. I view my nodes here with a small tree inside them as one node with big fan out. Right? This node up here, it has a small tree in it, is really one node with a bunch of children, right? And then I want to rebalance by splitting and fusing nodes. So this node I can split into two, or I can take two nodes and I can merge them into one. All right, so instead of doing rotations, I'm going to split and merge nodes. And that's exactly what B trees are. Okay? Actually, what I'm going to do is what is usually referred to as AB trees. Who knows AB trees? Not too many. Good. All right, so here are AB trees, so we'll go through them carefully. So a tree is an AB tree if it has all its leaves on the same level. Actually, all the trees I've been drawing for you until now has had all their leaves on the same level, right? They've been perfectly nicely balanced. But so B tree has all the levels on the same, all the leaves on the same level, and that's where the data is sitting in sorted order. Then all leaves has between A and B elements in them, and all nodes, internal nodes, has fan out between A and B, except for maybe the root. Okay, so here we have an example of a 2-4 tree. Each node here has degree between 2 and 4, 3, 3, 2, 4, and each leaf here has between 2 and 4 elements in them, the blue stuff. And I am assuming that A is bigger than 2 and B is bigger than 2A minus 1. Now, it should be pretty clear, I hope, for you that an AB tree uses linear space, right? It's a tree on top of the n elements. And it has height log base A of n. Why is that? Well, that's because the highest tree I can get is if I use the lowest degree, right? the lowest degree is A. So I cannot make a higher tree than the tree I get if I make all nodes have degree A. And that's a tree of height log A of n. Now if I choose the parameters A and B to be the block size B, then I actually get a nice tree like we looked at before, right? The leaves contains order B elements, and each node has fan out order B, which means they can sit in one block B, which means that I can go down through a tree using one IO in each node, spending log base B of n, and I can visit all the leaves when I'm doing a range search so that I report B elements every time I do an IO. Okay? So a B tree, an external tree, is just an AB tree where I've chosen the parameters A and B to be on the order of the block size B. Okay? Let's do that again. It's early, right? So I have a tree with two parameters A and B. All the nodes are sitting in the leaves in sorted order. On top of it, I have a tree. All leaves have between A and B elements in them, and all internal nodes have degree between A and B. Since the lowest degree is A, my tree is of height log base A of n. If I choose the two parameters A and B to be the block size, then one node can sit in one block on disk, one leaf can sit in one block on disk, and when I walk down the tree, I use log base A of n IOs, and A is the block size B, so that's log base B of n IOs. And for each leaf I visit in a range search, I report B elements, so I get the optimal query bound. And of course I use linear space because there's N over B leaves and N over B internal nodes. Okay? Now nothing I did here was different from what I did in the beginning, right? When I took the binary tree and just blocked it. I didn't really say anything. Yes, excellent. Uh-huh. Yeah. I want it to be balanced, yeah, right. Otherwise I can't get my query bounds. Yeah. Yeah. I meant any balanced search tree you can think of that is balanced by rotations, yeah. Anything else? Yes? Where you should. The elements are, they're sitting down here in the leaves in sorted order, yes. Yes, that's actually important. So they're not sitting up here. Up here you just have elements that guide your search, right? And if you're wondering, in here, in one node with big fan out, you actually have a lot of elements sitting, right? Because you need to be able to decide which one of the children you should visit. If you had a small tree sitting in here, it's sort of natural what elements you would have sitting. But when you have a big fan out here, you actually just have one element for each of the children, and you can sort of do binary search of what you want inside the node to figure out where you want to go. But it doesn't matter, right? Because I'm only counting IOs, right? I don't care how you figure out when you're standing here which one of these children you should visit, because it's all going to happen in internal memory. Good. Okay. Now let's see how we can then keep these trees balanced doing inserts and deletes. So inserts. Here's actually the whole insert algorithm. So when I want to insert an element, I search down the tree and I find where I want to put it, right? Now, what happens if I put an element here, for instance, in a node, in a leaf that already has the maximum number of elements? There's no room for it. So what do? Well, I want to split the leaf into two. And this can actually then recurse up the tree. So in general, I want to do, as long as I have a problem, I have a leaf or an internal node with B plus 1 elements, so one too many, I can split it into two nodes with approximately half of the elements. Okay? So imagine in here you're standing now with a node, or it could be a leaf, with B plus 1 children or elements, you split it into 2 nodes with approximately half of the children or elements each. Yeah? It's coming in a second. But here it doesn't matter. Except it does matter for one thing. Maybe. So no, let me finish up. I split this node into 2, but now its parent got one more child, right? So therefore, I keep going until I end up in a node that has less than b or b children, right? I'm standing here with a leaf. I split it into 2. Its parents get an extra. It might have to split into 2. Its parents got an extra. If it's okay, I stop. If it's not okay, I split that 2. And I keep doing this until I find a node that's okay. Or I hit the root, right? If the root contains b plus 1 elements, I split it into 2 and I make a new root. In any case, I only touch the height of the tree nodes, right? I go up one path of the tree. Now you asked about A. There's actually one thing that's important here, right? When I take this node V and I split it into 2, I want to make sure that it's nodes that are okay, right? What does it mean to be okay? They have to have at least A elements and at most B. They definitely have at most B, right? But what about A? Well, I chose A and B such that I'm sure that if I take B plus 1, a node with B plus 1 and I divide it by 2, I definitely get more than A. Right? So I know that both of these children here, or both of these nodes have more than A children. So they're okay. They're between A and B. Okay, so I stick an element in a leaf. If it's too many, I split it. If its parent have too many, I split it, and I keep doing that until I'm done. I can mostly travel to one path, so I most touch this many nodes. Good? Man, it's Monday morning, huh? I know you haven't been partying. You have been making homework all weekend, right? All right, let's do an example. I'm so proud of this animation here. So let's stick an element over here, right? I want to put an element here. I can't because it's already full. It's a 2-4 tree. What happens? Well, I split it into 2. That means that now the parent has 5 children. That doesn't work, so I split it into 2. The parent now up here got 1 extra, but it's okay, so I'm done. That was so cool, let's do it again. I split it into 2, the parent gets too many. I split it into 2, its parent is okay. At most it travels up one path. All right, deletes are more or less the same, just a slightly more complicated, right? I search down for the element I want to delete, I delete it. Now that node might have A minus 1 elements in it that leave, right? I could be in a leaf with A elements, I delete 1, so I have 1 too little. What do? Instead of split, I split before, so now I merge. When I merge, my parent gets 1 less child. That might be A minus 1 now, so I might need to merge him with somebody, and it continues. So let's do that in more detail. I'm searching for a leaf, and then as long as I'm in trouble, I do what we call a fuse. So here's a node with A minus 1 children. What do? I take its sibling, and I merge them into 1 new node. Now I know that this 1 new node has at least 2A minus 1 children, right? Or elements. Because it got A minus 1 from this guy, and its sibling here was okay. So it has between A and B. So it has at least A. So the new one I get has at least 2A minus 1. That's more than A, so I'm fine, right? The problem is that it could be more than B. But actually it could be at most 2B. It could be at most, if my sibling over here has B already, and I have A minus 1, then it's A plus B minus 1, which is less than 2B. If I have more than B, I just split it into 2 again, and I'm done. Right? So I look at a node, I merge it, My parents got one less. I could now be too big. If I am, I split it again. My parent got one back. And he has as many as he had before. So I'm done. Yes? Yes? Very good question, and I'm going to come back to it in 2 slides. Very good question, because it actually is important. So he's asking, but actually, the answer to what you just said was no, right? The merge can also travel up, right? It could be, if I end up splitting this node I just made, then it doesn't travel. But it could be that I don't split it and it travels up. Let's do an example. Let me delete something over here, I think, right? They have 2 already. If I want to delete one over here, I'm in trouble, right? It's a 2-4 tree, so it has to have between 2 and 4. Now this one only has 1. So I merge with the sibling. Now I'm okay, but my parent is not. So I merge with my sibling. I have this weird situation where, now I'm exactly in the situation where I got more than B fan out, right? We go back here. When I did the merge, and I'm okay, but my parent is wrong. Here I did the merge, and even I am not okay. I got too much now. But that means I can split again into 2, and magically everything is done. It's pretty cool, right? I mean, you can't imagine how long time I spent doing this. Merge, split, and we're done. It could actually travel all the way up to the root, right? And if the root ends up having 1 child, then I just delete it. Okay? Now comes the answer to your question. If I have an A-B tree where I choose B to be exactly 2A minus 1, which was the smallest that I allowed, then actually I can have that each insertion or deletion can travel all the way up. And I have an example over here. So this is a 2, 3, 3. Okay, so every node here has between 2 and 3 children. If I do an insert here, then this guy splits into 2, and this guy gets 4. He splits into 2. This guy gets 4. He splits into 2. It goes all the way up, right? So I go from a tree here where everybody has degree 3 to one over here where there's a path where everybody has degree 2. That means that I can now do an insert and get the opposite direction, right? Again, everything merge all the way up. So I can do this flipping back and forth where I insert and delete elements, and every time I do something, it travels all the way up. Okay, so every insertion or deletion can cause many rebalancing operations. Okay? We don't like rebalancing operations, as we'll see in a minute. So therefore we can do something else. If we just say that B has to be at least 2A, so just 1 bigger than this, then magic happens. Then we can actually prove that on the average, or amortized, each insertion or deletion can only trigger 1 rebalance operation. That's pretty cool, right? So I just got slightly a little more slack, and now things can't travel up every time. In fact, on the average, it doesn't travel more than 1. So sometimes it can travel a lot, but most of the time it only travels 1 or 2. In fact, I can do even better. If I go one further up and say, instead of B having to be at least 2A, it has to be at least 2A plus 1. Then I can actually show that on the average, I only do 1 over A rebalancing operations. So very, very seldomly I travel anywhere in my rebalancing. This, as it says here, it's somewhat hard to show. If I had 2 hours, I could. In fact, this, if you know about amortized analysis, which I hope you at least have heard about, then this paper that proves this was the first paper on amortized analysis that used the potential function technique. Okay, so this was actually the result that sort of the two results that defined amortized analysis, this result was one of them. And it's actually quite difficult to show, but pretty cool, actually. So if you want a challenge, go and read this paper. Mehlhorn and Huddleston. Somewhere in the 80s, sometime in the 80s. But actually, I need this result. So I'll show you another one which is easy. In fact, it fits here. If I say that instead of B being 2A, B has to be 4A, so I allow more slack, then I can easily show you a worse result than this. Actually, I could also show this result, obviously. But this result I can easily show. It says that on the average, only every A insertions, things travel all the way up. And it's easy actually to see. So imagine that B is 4A, and I do an insertion. And I do an insertion in a leaf that makes the leaf split. Right? When that leaf split, I get two new leaves that have approximately 4A divided by 2, so 2A elements. Right? I have a leaf with 4A elements, I split it into 2, so now it has 2A elements. It's going to be a while until I can make this leaf split or fuse again, right? I either have to put 2A elements in it to get up to 4A, or I have to delete A elements to get down to A, right? So it'll take me on the order of A insertions or deletions for the split to happen again. Similarly, I can argue for fuse that if I take two leaves and I fuse them because I was deleting something, then the new thing I get has between 2A, if I had two nodes with A elements in them, and 5A elements if I had one with 4A and one with A. And when I split that back, I get again something which is almost in the middle, or at least on the order A away from either of the boundaries. Okay, so now I've argued that when I do an insert or delete in a leaf that triggers a split or a fuse, it's going to be a long time until that new leaves can split or fuse again. Should be A insertions, right, or deletions. So that means that if I do n insertions, then I do n over A splits or fuses on the leaves. And since each of them can only travel all the way up, I get this bound. Okay? So here I'm basically just counting how many leaves do I create or delete, and then I say, okay, and they can travel all the way up, which is of course not true, but I just need this bound for a little later. All right, let me summarize so you can get back on here if you dropped off. Okay, so a B tree is basically just an A-B tree with parameters, both of the parameters chosen to be the block size. It uses linear space. It can answer queries in what I want, namely an optimal search bound log-based B of n plus an optimal output bound. And now I can do updates in log-based B of n, right? Because everything we did when we did insert and delete touched one path of the tree. And one path of the root leaf path is of height log-based B of n, so it uses log-based B of n IOs. Okay? So now we actually have a nice external search tree that has all the properties we would like: linear space, logarithmic query, and logarithmic update. And actually, if you think about it, even though it might have sounded complicated here on a Monday morning, it's actually a nicely simple way of balancing search trees, right? I'm just splitting and fusing nodes. The alternative is to rotate, right? Now, everything I said, and we talked about it, was we said that the elements are in the leaves. Sometimes, just so you know it, because you might meet the term B plus tree. So in the database community, they like coming up with a new word for each data structure they make, right? So a B tree for them is a tree where the elements are sitting all in all the nodes. And a B plus tree is one where the elements are only sitting in the leaves. I only have them in the leaves, so they're called B plus trees. Sometimes. Yes? Yes, yes, but if I do that, then I rebalance every time, right? I mean, if you insert, then it splits, and I take care of it, right? And you keep inserting in the splits, and every time I take care of it. That was this. Oh, am I not getting your question? That was this example here, right? I mean, you say I insert over here, and it can split. And if I now insert here, I can again make it split, right?
But does it mean that the tree is actually, in this example, the right branch of the tree can grow?
Yes.
The left branch of the tree?
Yes, yes, yes. And what's the difference between the height of the no, what's the height of the tree? It's a good question, so we're going to let it stand for a second. Actually, it looks like it grows, but it doesn't, right? I mean, it's the same height all the time, right? The leaves are on the same level. The fan out in different nodes are very different, right? Over here you have one of degree 2, here you have one of degree 4. On the other hand, underneath it, there's a bunch of them that have a fairly low degree, whereas over here there's one that has big degree. And actually, we're maintaining that all the leaves are on the same level all the time. So you're right that you can have sort of subtrees in between that has very different degree, but they're all going to be height log base A of n at the highest, right? The highest tree I can get if all the nodes has degree A, the smallest degree. The lowest tree is if they all have degree B. But since I choose A and B to be more or less the same on the order of the block size, it doesn't really matter that much. Okay? Let's get back to the, here we were. Okay? Before we take a break, let me just mention a couple of more things to you. We talked about, we can now build a search tree, right, by inserting the elements one by one. But actually, we can also build it easily bottom up, right? If you have n elements and you want to build a B tree, you can sort them using this bound. Now you have the leaves, and then you can build the tree bottom up afterwards, one level at a time. And that's going to take you this many IOs. I'm just going to generalize this slightly, not much. I'm going to introduce a notion where I call a B tree with branching parameter B and leaf parameter K is basically a B tree, except that I allow the leaves to have a different number of elements than degree. That's going to be handy in a minute. So a B tree with branching parameter B and leaf parameter K has exactly, it's the same as a B tree, except that in here I say that the leaves I can have between 1/4 K and K elements, and all other nodes have degree between 1/4 B and B. Okay, so I'm basically saying the K decides how much wiggle room I have in the leaves, and B decides how much I have in the degree. But other than that, it's exactly the same. And if you choose the leaf parameter to be the block size B, then you of course get a tree like this. And the only thing I really need for later on is this bound here. This was the bound we talk about on how many splits happen. And we just argued that it was the 1 over the number of elements in the leaves times the log, the height of the tree. And that's basically what it says here. It says 1 over K, which is the leaf parameter. And then it says 1 over B also. But that's because I just make the same argument one level up. And then that can travel up. It's not really so important. It's just you got to know that I can later on claim this and use it. That's all. This here just says that the number of rebalancing operations I do is 1 over the leaf parameter and 1 over the degree parameter times the log, the height of the tree. All right, so one more minute and we'll go to break. Normally when I do when I have a search tree, which we do have now, an optimal search tree, then I can also have an optimal sorting algorithm, right? I said that at the very first lecture also. If I want to sort n elements, I can do that in n log n time by inserting them one at a time and deleting them all one at a time. Since an insert and delete takes me log n time, then it's going to take me n log n time to sort. If I do the same thing with a B tree, I get this bound, right? N insertions cost me n times log base B of n. N deletions afterwards cost me n times log base B of n. This is not the sorting bound, right? The sorting bound is this guy, right? In fact, this bound is way off optimal. This is a factor of this much from optimal, where the important part is this B, right? I'm missing a B below this N here. So this was this thing I said way in the beginning, that even though I now have a optimal search tree, I cannot use it in an optimal sorting algorithm. You're used to being able to do that, but you can't. If you should have a sorting algorithm like this, you would have to be able to do each operation in this many IOs, right? If you could do an insert in this and a delete in this, then you could do n insertions followed by n deletions, and you would get this bound. So really what I would like is a search tree where I can do operations in this bound. This is obviously smaller than log base B of n, right? Smaller than log base B of n. And I claim that log base B of n is optimal. So I can't actually get this bound. There's another reason why this bound looks weird. And that is, for practical purposes, it's less than 1. B is very, very big. This log is very, very small. So here says something that's 1 over something big. So it says that I can do inserts and deletes without doing IOs, which seems counterintuitive. Nevertheless, after the 10-minute break, I'm going to show you how to get this bound, even though I just claimed that it's impossible. All right, so let's take a 10-minute break. So now we saw B trees, or these trees with big fan out, where I rebalance by splitting and fusing nodes, and I got this nice log base B of n update and query bound that I say is optimal. But as I just argued, to get an optimal sorting algorithm, or I cannot get an optimal sorting algorithm if I just stick n elements into a B tree and pull them out again. I actually get an sorting algorithm which is highly non-optimal. If I wanted to use a search tree for optimal sorting, I needed one that does updates in this bound. So actually, I'm going to now show you how to get this bound. But since I said that log base B of n is optimal, it's going to come at a cost. And for a long time, you're not going to realize what that cost is. So be prepared that at some point I'm going to ask you what the cost is. How can it be that I can get this bound when I claim that a worse bound is the best I can get? So here's what I'm gonna do. Maybe I should tell you here how easy it is to get a PhD thesis. So I basically had, don't tell this to anybody, but basically I had 2 good ideas in my PhD thesis. This is one. And the other one was multi-slabs, which you saw the other day. And then I wrote a handful or more papers on that in various contexts. But, but this is all it takes. It takes 2 good ideas. So here's one. Buffers. So here I have a B tree. And remember, to get from a binary tree to a B tree, all I did was to block it. Right? I took a binary tree and I blocked it breadth first search, and I got a B tree. Now I'm going to just do the same thing one more time. So I'm going to block these things now, not B-wise, which I can't because they're already of size B, but I'm going to make blocks of size M over B. Now they don't fit in a block, right? So this is all something I'm going to do conceptually. Okay? So they're not actually sitting out on a disk in block like this, because that's way more than a disk block. But I'm just going to think about doing this blocking. And then I'm going to assign each of these blocks here a buffer of size m. Okay? So I group the nodes together. I think about grouping the nodes together so that one of these mega blocks here has fan out m over b. That means that if you look at the height of the mega block tree here, right, it has this height, which we saw this log we've seen before. And then I give each of them a node, a buffer of size m. What I'm now going to do is that when I want to do an update, in a B tree I would search down the tree, right? Do an update and then rebalance. Here, I'm just going to be lazy and I'm going to stick it in this buffer here. So I'm just going to put an element in the buffer of the root saying, eventually you should do this insert and delete, or delete. Next time I do an insert or delete, I also put it there. Next time I do an insert or delete, I also put it there. Eventually this buffer is going to be full, right? It's going to contain m elements. When it's full, then I'm going to take these m elements and I'm going to push them one level down, and only one level. Okay? And put another way, I'm going to take these m elements and I'm going to distribute them between these buffers on the next level. So these m over b buffers on the next level. The way I'm going to do that is I'm going to take these, load them into memory. They fit, right? There are only m of them. I'm going to sort them, and then I'm going to put them out here again as I want. I will argue, actually I can argue now, that that process costs me m over b IOs. Why does it cost me m over b IOs? Well, I have the buffer of m elements. I load them into memory. M elements takes me m over b IOs to get them into memory. Then I sort them, and then I put them out again to the children. Putting them out would cost me m over b if they were nicely blocked. But I can't be sure that they're nicely blocked, right? Could be that one element goes here, but I have to spend an IO putting it there. One element goes here, but I have to spend an IO putting it there. Many elements go here, so I have puts a lot of elements here, and so on. But it's easy to see that you can at most spend m over b IOs, which is the time IOs it takes to write them, plus one IO for each of these buffers that are not full, right? And since there's m over b of them, I can at most spend m over b IOs plus m over b IOs. So it's order m over b. So yeah, I'll get this is just an overview. I'll tell you exact definition in a second. I'm trying to just convey the idea here. Then I'll answer your question in a minute. So the idea is just that I take my tree, block it into these supernodes, give them a buffer each. Instead of searching all the way down the tree to do an insert, I just plug it in the root. When I've collected a lot of stuff up in the root, I push it one level down. I can push these m elements one level down using m over b IOs. That's 1 over b IO per element, right? I take m elements, put them one level down in m over b IOs. It's going to be 1 over b IOs per element. Or put another way, each block of elements costs 1 IO to come one level down. Now, if any of these buffers on the next level are full now, then I also take those and I push them down, right? So every time a buffer runs full, I push the elements one level down. But every time I push elements down, I do it blockwise. So I touch each block of elements one time on each level of the tree, since the big tree, since the tree is this height, and I spend 1 IO per block, I have this many blocks if I insert n elements, so I spend this many IOs. What am I really doing here? I'm doing this trick of, instead of for each element spending 1 IO on each level of the tree, I'm grouping them together so that they can combined help each other pay, right? Right? Instead of one element spending 1 IO on each level of the tree, I group them together so that B elements can pay that 1 IO. And I also make sure by by doing this extra blocking that you don't pay on log base B levels, you only pay on log base M over B levels. So I'm being lazy. I'm being lazy, but that allows me to group many things together. And when I do an I/O, it's not just to move one element, it's to move a lot of elements. And that's exactly what you want to do in I/O efficient algorithms all the time, right? You don't want to do stuff on one element. You want to do stuff on a lot of elements at one time. You look very puzzled, so let's do it again. But now we do it in the glory details. Okay? So now we start over now and we do it all again. Here's what it really is, a buffer tree as we call them. It's a B tree with branching parameter M over B and leaf parameter B. So remember that means that the fan out of the tree is M over B, between 1/4 M over B and M over B, and the number of things in the leaves is B, between 1/4 B and B. So it's just a B tree, to answer your question, except that the fan out is big and the leaves are smaller. And one extra thing, I've assigned a buffer of size M to each node. But that's all it does. It's a B tree with a buffer in each node. Okay? Now to do an update, you come and say, do this insert, Lars, and I say, okay. I give the element a timestamp. Why do I give it a timestamp? It's because since things are happening lazily, I can actually have the same element floating around several places in the tree, right? Because you can do an insert of an element, then delete it again, then insert it again, then delete it again, and they're all floating around. So you need a timestamp to keep track of how were they ordered. But we can forget it for now. All right, then I collect B elements in memory. Once I have B elements in memory, I put it in the root buffer. Why do I collect B elements in memory? Because I don't want to spend an I/O per element, right? So I wait until I have B of them, and then I stick it here. If this is full, I'm going to do a buffer emptying. Buffer emptying in this process of taking these M elements and pushing them one level down. So let's see how in detail we do that. Before we do that, two notes. I hope it's clear to you that actually when between buffer emptyings, buffers can actually get very, very big, right? If this buffer here is full and I push the elements down here, it could happen that they all go to this buffer, right? If this was almost full already, this is now very full. It contains 2 M elements, right? If I now empty this and push it down here, it could be that they all go to the same buffer, which now could contain up to 3 M elements. So things can really cascade as we go down. Buffers can become very, very big while we are in the process of emptying them. But I can actually distribute these elements in sorted order. So if I have a buffer that's very, very big, 24 M, it's only the first M of them that are not sorted. The ones that sort of dribbled came down in several buffer emptyings. The ones that came from up in the parent node right now, they can come in sorted order. It's going to be important in a second. The other thing I want to say already now is that I didn't talk anything about rebalancing, right? And actually that's where the tricky parts are. So what we're going to do is we're going to do buffer and emptying in all the nodes that needs to be emptied, right? The root empties, and that triggers other needs that needs to be empties, that triggers other thing that needs to be emptied. Eventually I'm going to hit the leaves. When I hit the leaves, I need to do some kind of rebalancing. I'm going to put that off until I've emptied everything else. So I emptied all the buffers that I need to empty, and then I go and look at, oh, did I need to do something down in the leaves? And I'm going to show you now both. How do you empty internally and how do you empty the leaf nodes? Here's the internal nodes. This is basically what I said already. All right, if this buffer here is full, it contains M elements. It could contain more than M, but if it does, they're all sorted except for the first M. I load these first M that are not sorted into main memory and I sort them. Then I merge them with the other ones out there that are sorted already. So now I have a list of sorted elements, right? Those I just run through, I scan through them, and I remove matching insertions and deletions. That's this thing. If I have an insert of an element and a delete of the same elements, and the timestamps match, right? The insert happened before the delete, then poof, they disappear, right? That's how actually I do deletes. When an insert meets a delete, they die. So that I do here. If they meet each other, they're going to end up next to each other because I just sorted, right? And then I distribute them to these children just by saying, okay, I have these in sorted order. I run through them, put the first one that needs to go here. Once I'm done, I move here, 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 and so on. If any of these are now full, I recursively empty them. Okay? I will argue that if this buffer here contained x elements, it takes me x over b plus m over b IOs. Why? Well, what do? I start by loading the m elements into memory and sorting them. That costs me m over b. Then I merge with the rest. That costs me x over b. Then I distribute them to the children here. That costs me x over b for every full block I put here, plus maybe one non-full block for each of these children. But there's m over b of them, so it costs me x plus over b plus m over b. Since I only do this if the buffer is full, namely that it contains more than m elements, this is x over b. So this really means that if there's x elements in this buffer, I spend 1 over b IOs on each of them to push them one level down. Was there a question? Yes, x has to be greater than m, right? I'm only doing this buffer emptying if the buffer is full, so x is bigger than m. And actually, it's a good question in the sense that note that if x was smaller than m, this would cost me not x over b, but m over b. Okay? So if I'm pushing x elements down, if x is bigger than m, it costs me x over b, 1 over b per element. If x is smaller than m, it costs me m over b. All right, so that was emptying buffers inside the tree. Now I still need to see what happens if I'm down by the leaves. And that's sort of where the nitty-gritty, ugly details are. This can actually be handled in many ways. Here's one way of handling it, where I try to not optimize complexity, but optimize explanation. So it should be understandable. All right, so if I'm standing here, this buffer is full. I've emptied all buffers that are not above the leaves. Now it's time to do these buffer emptyings of these kind of guys that can trigger rebalancing. What do? Well, I sort this buffer as I did before, right? Take the first m, move them in, sort them, merge them with the rest. So now I have these elements in sorted order. Then I merge them with these elements down here, right? Down here there's a bunch of elements in sorted order. Up here there's a bunch of elements in sorted order. I merge them. Some of these elements are insertions, some of them are deletions. So some of them gets in the order, some of them removes elements that are in the order, right? So I end up with some number of elements. Let's call it k prime. Right? So if I had k elements here to start with, I end up with k prime elements afterwards. K prime could be smaller than k, or it could be bigger than k, depending on how many inserts or how many deletes I had. If k prime is smaller than k, meaning I deleted a lot of elements, then for now I'm just going to stick dummy elements in there so that it looks exactly like it did before. Because I don't want to deal with deletes right now. Deletes are difficult, so I don't want to deal with them. So I started out in a situation like this. I end up in a situation like this where the buffer is empty by sticking in dummy elements. If, on the other hand, I have a lot of insertions, so I have more elements than I started with, then I'm actually going to start putting them in there. And I'm going to put them in here in the leaves, and I'm going to insert them a block at a time. So I collect the block elements, insert them, and then rebalance. Once all of this is done, and I only are left with leaves that have these dummy elements in them, then I delete those too. I'm going to tell you in a second how to do this. But before I do that, let's look at the insertion, when I insert a block. It's actually very, very easy because of the stuff we've done already. We will have it on this slide here. When I do an insert, I just do like I would normally do in a B tree. Remember when we did an insert in a B tree, we stuck in a leaf, and then if the parent now has too many children, we split it. If that parent has too many children, we split it. Now that's actually very easy now because I maintain the invariant that when I'm standing in a leaf where I put in an element, all the buffers up to the root, they're actually empty. So it looks exactly like a B tree. Why are they empty? I just emptied them, right? Yeah. But you would imagine how difficult it is to understand the first time. Right? I emptied the root, that emptied the child, that emptied a child, that emptied a child. Eventually I came down to the to the leaves. That must mean that they're all empty all the way up. Because of the way that I did this, right? I made sure to empty everything before I start on the leaves. So that means that when I do insert of a block here, I just do exactly like in a B tree. I stick it in there and then I split elements like I need to do. I don't need to worry about this being a buffer tree with buffers because they're all empty. Deletes are slightly more complicated, but not much actually. And this is why I want to do them using this dummy element. When I want to delete a block of elements from the leaves, I want to merge nodes, right? But there my invariant actually don't give me that I have empty buffers, right? You see this node here, you've deleted something down here. Now you would like to merge this guy with this guy. But it's true that this guy and this guy have empty buffers, but this over here might not have. So, and if I start merging these, I can get in some nasty problems where I've already merged emptied stuff underneath it, but I'm not done because I can have other dummy elements and stuff. So to get out of this situation, before I do this merge of these two nodes, I just empty this buffer. Okay? I empty this buffer, and then I do the merge. And now we're in this situation where we're emptying a buffer with less than m elements in it. We should remember that, right? But actually, luckily, it's not a problem. Here comes the analysis. If we don't count all the stuff going down in the leaf, like I just talked about, my argument from before that when I empty a buffer, it contains more than an m elements, so we pay 1 over b per element, actually exactly gives me the sorting bound. That was my very first slide. All I need to argue is the elements in the leaves. When we do this delete of dummy elements, we end up emptying buffers. And we empty a buffer every time we want to fuse a node. That is a buffer that has less than m elements in it, so it costs me m over b IOs. So one fuse costs me m over b IOs. Let's just say that all rebalancing operations cost us m over b IOs. Luckily, I can argue that I don't do too many of them. That was this one bound that I promised you that I would use, right? Here I have a B tree with leaf parameter B, branching parameter m over b. That means that I have this many rebalancing operation over in insertions. That was just an application of the bound we had on the earlier slide. Since they each cost m over b, I have to multiply this with m over b, and I get exactly the sorting bound again. So even though a split or a merge, a fuse cost me a lot, it doesn't matter because I don't have a lot of them. So here you see an example of where it's important to have slack in your B tree and not do very many rebalancing operations because they're expensive. But the bottom line here is to do n insertions or deletions, I spend this many IOs, so amortize each of them costs this divided by n. Now, I did all this because I wanted a sorting algorithm, right? I want to be able to insert n elements and pull them out again and get them in sorted order. But actually I can't just do that, right? Because if I've inserted n elements, I have elements sitting all over the place in this tree. They're not sitting in sorted order in the leaves because they could also be in the buffers. So to sort, I actually need to empty all the buffers. But luckily I can just empty them one at a time from the top. If I empty all the buffers, I start emptying this guy, then this guy, this guy, this guy, and I empty them all, and eventually they're all going to be down here in sorted order. And it's easy to argue that it's going to cost me a linear number of IOs because how many buffers do I have? I have this many buffers. I pay M over B every time I empty a non-full one, so this times this is linear, so I can empty all these in linear number of IOs. So now I got another sorting algorithm. So here's the summary. I now have a search tree where I can do inserts and deletes in this number of IOs, which means that when I do n insertions and empty all the buffers afterwards, I get another sorting algorithm. So now you see merge sort, distribution sort, and you can also do buffer tree sort. Now comes the question that I promised you. How can I do this? How can I get a bound that's smaller than log base b of n when log base b of n is optimal? Yeah? Exactly. I can't search in this thing, right? If you ask me to search for an element, I can't do it, right? Because if I should go down to a path, I meet all these buffers that are very, very big. I need to look at all the elements in the buffers, right? To see if it should be there, the one I'm looking for. So the reason why I can do this is that I can't search anymore. So I'm beating the lower bound by throwing away its functionality. But wait, I can. I can actually do batch search. I'm not going to tell you how, because I'm going to tell you this much about how. I can actually implement a range search operation, meaning give me everything between two elements. Batched. So it's an operation where you ask me to search for something or report elements between x1 and x2, and eventually I'm going to give them to you, but not right now. Right? Normally in a search you ask, search for this, and you go and search and you come back. Here you ask, search for this, and I promise that eventually I'm going to answer the question. And I might actually answer it sort of a little at a time, but eventually I'm going to answer it. That you can implement, and you can actually get the same bound. You can answer a range query, so finding everything in between two x's, in the same search bound plus the output size divided by b. And the way you do it is exactly like with the insert and delete. When you want to do a range search, you stick a range search element in the root buffer. And then as it travels down the tree, you report stuff along the way. That means that you are going to report stuff sort of at different times when other inserts and deletes and searches come along. But eventually you're going to answer the whole thing. I see some smiles around thinking why this doesn't make any sense, that we ask a query and then we don't know when we get the answer. But actually, here's one application where it really works. Remember we said when we did distribution sweeping, the first problem we looked at was this, you remember, I'm sure, this segment intersection. And I said, I can't do the sweep because every time I hit a segment, I want to do an insert, delete, or a search. I can't do that because I'm going to spend an I/O doing it. Instead, I have to do distribution sweeping. But now I can actually do it. Right? I just run the exact normal sweep algorithm. When I meet a top segment, I do an insert. When I meet the bottom, I do a delete. When I meet a horizontal segment, I do a search. But I do it on the buffer tree. Right? Inserts and deletes cost me this. Search cost me this. If you multiply those two with n, you get the bound that you want. So actually, these buffer trees gives you another way of solving these geometric problems without doing distribution sweeping. Why does it work here? Well, it works because I don't care if the search is batched, right? When you ask, when the query is here and you ask this query with this segment here, getting these intersections here, you don't actually need them right away, right? As long as they come at some point, it's okay. Okay, so these problems are these problems called batch dynamic solutions, that they're dynamic, but they're batched in the sense that you don't actually, the dynamic inserts and deletes don't depend on the answers to the queries. So it doesn't matter when you get the answers to the queries. Good. I can also do a priority queue. Okay? How do I do a priority queue? Well, you're used to having a priority queue I can implement with a search tree, right? Right? If I have a bunch of elements with priorities, I stick them in a search tree. Now I know that the minimum priority is going to be in the leftmost leaf, right? It's going to sit here. So when I want to do a delete min, I just go and get it here. That's also true in the buffer tree, almost, right? If I have a buffer tree and I've done a lot of the insertions, I want to do a delete min, it's sitting down here, right? No. It could also be sitting in any of these buffers here, right? I don't know where the minimum is. It could be down here, or it could be in any of these buffers. So what do? Well, I just empty all the buffers. Okay? When I want to do a delete min, I empty these buffers one at a time. Now, when these buffers are empty, I know the minimum sits down here, right? Not only do I know that, I know the second minimum sits right next to it. The third minimum sits right next to it. So what I do is I delete all of these guys down here, and then there's going to be 1/4 m of them, and stick them in main memory. Right? Next time you come and say delete min to me, I just give you the one that's sitting in memory without doing any IOs. Next time you ask delete min, I give you the next one in memory without doing any IOs. I can keep doing this for order m delete mins, right? Except, of course, if you do an insert of a small elements in the meantime, right? But if you do an insert of a very small element, you compare to the ones you have already in memory. If it's smaller than one of those, you just kick one of them out and put it in there instead, right? In any case, you can now answer m elements, m delete mins, for free. So the question is, how many IOs did you use to be able to answer these m delete mins for free? Well, you used a buffer emptying on each of these here. A buffer emptying cost m over b. There's this many buffers on the leftmost path. So you spend this many IOs every m times you want to do a delete min. So that's this much amortized. Same bound as before. And this is actually funny, right? Because this is not batched. Here you do a delete min, and you get the result right away, not eventually. You get the result right away. Sometimes you actually get it very, very fast because I have it in memory. Sometimes it takes a long time because I need to empty these buffers, but you get it before we do another operation. All right? So I actually have now a priority queue where I can do insert and deletes and delete min in this bound, amortized, beating a log-based B event bound. All right. So, yeah. So, you know, in an American baseball game, in the 7th inning, we sort of stretch a little bit because we're tired. I think we need to stretch now, right? Now we have priority queues. Now I'm going to, the last 15 minutes here, show you a very important application of this priority queue. But you can wake up now if you want, because now we are not doing blocking and buffers and anymore. We're just going to use the data. We have a bunch of data structures now. Now I'm going to show you one neat application of it on a completely different problem. But a problem we've seen before, list ranking. So the simplest problem, the simplest graph problem you can think of. Okay? It was the problem I used in the beginning to tell you how block size is difficult, or important, right? This thing about seconds or hours to solve a problem. So here's the problem. If you forgot, you have an array that stores a linked list, and it stores it just by saying each entry points to another entry by storing the index of that entry, right? So here it says 3, meaning I point to element number 3, I point to element number 5, I point to element number 8, that points to element number 2, and so on. So I have a linked list stored in an array. And all I want to do is traverse the list. Okay? Or pull the list and sort it, right? I want to traverse a linked list. So I said it's one of the simplest graph problems you can think of, right? It's a linked list, so it's a graph. It's straightforward to do that in a linear time, right? You just traverse the list, spending one time unit on each. That would also cost you NIOs. because you jump around in a list, right? Every time you follow a pointer, you spend an IO. I'm going to show you how to do it in the sorting bound. And it's going to take us 15 minutes. So that should indicate to you that the simplest graph problem I can think of is difficult. Meaning difficult graph problems are really difficult. In fact, we don't know that much about graph problems in external memory. There's lots of results, but none of them are very satisfactory. This is actually the best I can do, so we're satisfied here, but the algorithm is quite hard. No, it's not hard, it's just a little tedious. So let's try and see if we can do it. You're with me on the problem, right? Just number the list, number the elements in a linked list. Actually, I'm going to solve a more general problem. I'm going to solve the problem where the edges have weights. Okay? So on each edge, there's a weight, and what I want to do is I want to sum up of the weight to my node, right? So if I try again here I'm summing up the weight all along the way, but since they're all 1, I get list ranking. But some of these ones here could be 2s or 3s or 27s, and I wanted to sum up the numbers along the list. Okay? Problem clear? I have a linked list, weights on the edges. I want for each node to compute the sum of the weights from the beginning to that node. All right, here's how we're going to do it. Now I'm drawing the list like it's sitting linearly like this. But it's not, right? Because if it was sitting linearly like this, it was very easy to solve the problem. I would just scan through. But I can't explain it without drawing it nicely here. So here's what I'm going to do. I'm going to find an independent set of vertices. An independent set is a set of vertices, the blue guys here, that don't have edges to each other. Okay? So none of the blue guys have a predecessor or successor that's also blue. Then I'm going to bridge out the independent set. That was this process that just happened on the slide here. Okay? So this guy here is going to be removed, and there's going to be an edge from his predecessor to his successor, and it's going to have weight that is the sum of the two weights. So I get this. Okay? Then I'm going to recursively rank that list. That gives me this result. Right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then I'm going to bridge back in the independent set. If you have seen parallel algorithms, you know exactly what I'm doing, right? If you haven't, you're learning. Now the trick here is that I'm going to show you that I can do step 1, 2, and 4 in the sorting bound. So I can find the independent set in the sorting bound. I can do this bridging out and the bridging in the sorting bound. Now if I could make sure that the independent set is of size alpha n for some constant alpha smaller than 1, then the recurrence for this algorithm is T of n is the recursive call on 1 minus alpha n elements plus the sorting bound, which gives me the sorting bound. Okay? So I have two things I need to show you now. I need to show you that I can find the independent set of some fraction of the elements, and that I can do the bridging out and the bridging in the sorting bound. If I do that, then I get a sorting algorithm. Okay? Finding an independent set, removing the independent set, recursively solving the problem, putting the independent set back in again. I get the right bound if I can find a very big independent set. An independent set that is a fraction of the element. Let's do the bridging out first. And I don't want to do the bridging in, because that's the same, basically. So in the bridging out, right, I was doing this process here. For each independent vertex, I was taking its predecessor and pointing it directly to the successor. So that's kind of this problem up here. I have a red node that has a successor in an independent set. What I want to do is make it link directly from the red to the green. So up here, if 8 is in the independent set, its predecessor is 5, it should point directly to 2. How do I do this? I do the following. First, I make a copy of the list. I was in an animation mood when I made these slides. I make a copy of the list. All right? Then I take the original list and I sort it by successor. This list looks weird, so let me remove the errors. For the important thing here is that when I sort by successor, then the red guy is going to end up in the position of its successor, which is the blue guy. Right? So the red guy ends up in the position of the blue guy because I sort by successor. Right? That means that if I scan these two lists in the same order, right? I take them and I sort them, scan them. Then when I meet the red guy up here, I eat the blue guy down here. Then I can see, the blue guy here points to the green guy. I can write that up in the red guy, which is exactly what I want, right? I want the red guy to know the successor of the blue guy. And there now, that information is next to each other, so I am getting it. And then I sort the list back, and I'm done. We sometimes call this primitive sort merge. That in a graph, we can get information about our successor or predecessor by sorting and merging a few times. So I can do this bridging out by sort merge, and I can also do the bridging in by sort merge. And it takes me the sorting bound, right? Because I did 2 searches and a scan. All right, so I promised you over here that I would do step 1, 2, and 4. Now I've done step 2, and step 4 is the same in this bound. Now we need the independent set. Okay? Independent set. It's easy to do randomized. If I flip a coin for each element in the list, and then I choose the independent set to be all the elements where I got a head and my successor got a tail, then I get an independent set, right? Because all the heads, you can only get an independent set if you're head, and if your successor is tail, then he can't be in the independent set. And I expect the size of that independent set to be n over 4, right? So alpha to be 1/4, right? Because if I should be head and my successor should be tail, then there's a half probability of each, and then they're independent. So the probability of me being in an independent set is 1/4. So that's easy, and I can easily do that in a scan. But of course, I want to do it deterministically. So I want to be able to find the independent set without doing randomized anything. And what I'm really going to do is that I'm going to find a 3 coloring of the vertices. What is a 3 coloring? It's a coloring of the vertices so that with 3 different colors, so that no 2 vertices, 2 neighbors have the same color. Why is that easier than finding the independent set? It isn't, but this is what I'm going to do. I'm going to find an independent set, a 3 coloring, and then I'm going to choose the most popular color as the independent set. That's going to be at least n over 3 of the vertices, right? If I color all vertices with 3 colors, and I take the one that has the most colors, it's got to be at least a third of them. And it's an independent set because there's no 2 vertices next to each other that have the same color. If I can do that in the sorting bound, then I'm done. Then I found the independent set in the sorting bound. All right, so now we're down to 1, we're almost there. We have 1 problem left. We want to color nodes in a list with 3 different colors. Here's what I'm going to do. I'm going to look at forward lists and backward lists. And here In my standard example you've seen a bunch of times, all the forward lists are on top and the two backward lists are on the bottom. Right, you can see there's a list starting here that goes forward here and then it ends. There's another one here that starts here and goes forward, ends. Another one that goes here, and down here I have two. So I have a bunch of forward lists and a bunch of backward lists. Notice that one node is in a head of one list and in the tail of the other list, right? Here, 3 here is the start of this forward list, but it's also the end of a backward list. Okay? Now I'm going to color the forward lists alternatingly red and blue, starting with red. So here it comes. 3 is red, 5 is blue, 8 is red, 4 is red, 9 is blue, 7 is red, and so on. Okay? So the forward lists I color red and blue. Let's do it again. It was so cool. I color them red and blue, starting with red. And I'm not coloring the tails. And the backwards lists, I'm then going to color blue and green, green and blue, starting with green. Okay? That's a 3 coloring. Why? I claim that none of these elements have neighbors of the same color. Which of them could have neighbors of the same color? Only the head and tails, right? Going forward, I do red, blue, red, blue, red, blue. Going backwards, I do green, blue, green, blue, green, blue. The only place where it can go wrong is at the end, right, where I have one going forward and one going backwards. Why does it not go wrong? Well, when I start a tail, it's always green. It can only have a blue or red predecessor, right? It cannot be green. And the successor of it can only be blue or red. The end of that list can only be red, because that's the start of another list. Okay? So it's a 3 coloring. So now I only need to show you how to color a list. And I'm only going to show you how to color the forward list. Right? The backward list we can color the same way. This is the last slide. All right, how am I going to color these? First, I'm going to figure out which ones are the heads or the tails, the marked ones here. How do I find out if I'm a head or a tail, or a head? Sort merge, right? I need to figure out some information about my predecessor and my successor. I can do that with that primitive we did before. Then, for each head, so for each start of a list, I insert a red element in a priority queue with a priority of the position of the element. I've tried to mark it here. You see there's a little red boundary around here. These 3 are heads of the 3 forward coming lists. This one, this one, this one. So now there's 3 elements in my priority queue corresponding to these 3 elements, and they're colored red. Here's my algorithm. I repeatedly extract the minimum elements from the queue. First it's going to be this 3 here. There's a 3 coming out of the queue with color red. Then I access the same element in this list here, and I color it, the color it should be, there. And then I put a new element in the priority queue with the opposite color, blue, corresponding to its successor. Right, you look puzzled, so let's try again. I find all the heads, that's 3, 4, and 7. I put elements corresponding to in the priority queue. Now, I repeatedly extract the minimum. The minimum first is 3. I color it red, and I insert the successor in the priority queue colored the opposite color, blue. The next thing I get out of the priority queue is the 4, right? I colored red, and I inserted successor 9 in the priority queue with blue. The next thing I get out is 5. I colored blue, and inserted successor in the priority queue with red. And I continue doing this. What happens, as you can see, is that I actually traverse this list just going forward, right? I'm just traversing this list going forward. I can do that IO efficiently, right? So what I'm really doing here is that I'm doing a scan of this list to do the coloring, and then I'm doing n priority queue operations. That I can do in the sorting bound. So the priority queue here makes me traverse this list efficiently. And it does it by sending these colors sort of forward, right? When I color a node, I say to its successor, eventually you should be the opposite color. I don't want to go and color you right now because I can't. That's going to cost me an IO. So I'm going to do it a little later. But I'm turning n accessors, these n accessors to the list, I'm turning that into n priority queue operations. And therefore I get the sorting bound. So summary, and then I'll let you go. Get some coffee. I solved this list ranking problem, the simplest problem I could think of. It's easy in internal memory. It takes me n time just by visiting them one at a time. I hope if you didn't get anything other out of this lecture, you got out of it that it's hard in external memory. And it involved these finding independent set, which involved finding 3 coloring, which uses a priority queue to traverse the list. And actually, it's optimal, because I think you can argue, we can agree that when I'm traversing a list, what I'm really doing is that I'm doing a permutation. Right? I'm at least finding the permutations, or you can do a reduction. You can try it at home. You can do a reduction to the permuting bound. So actually, this is optimal. You can't do any better. I want to just say a little bit high level here, namely that for those of you who've had PRAM algorithms, so parallel algorithms, will recognize this. This is exactly what you do in parallel algorithms, at least the idea. And in fact, we sometimes in external memory refer to this as PRAM simulation. So you take a PRAM algorithm, you take a parallel algorithm, and you simulate it in external memory. But more importantly, what I did, this thing about using a priority queue to traverse a list, is a primitive that we use a lot in external memory, and we call it time-forward processing. This is this idea of sending information forward in time. Right? What I did in the list was when I colored a node, I told its successor forward in time that it should be the opposite color. The way I did that was by inserting an element in a priority queue. So this is, when I go and drink with other IO efficient algorithms, we sit around at night and throwing terms like time forward processing around, right? And we all know what we're talking about. So this is one of these things that we all say, and it can mean a lot of different things, but it's this idea of sending things forward in time using a priority queue. Here's what I covered today. The cache oblivious stuff was here. I think the best place to read all the other stuff I talked about was, I have a survey on data structures, and Norbert C., who's the expert in efficient graph algorithms, has a survey on graph algorithms. And everything I say is in the beginning of those surveys, which you can get to from my homepage. So here's what I did. Sorting, hardness of permuting, batch, geometric problems. We saw a bunch of search trees, B trees, buffer trees, priority queues, graph algorithms, list ranking using the priority queue, and we also saw a little cache oblivious algorithms. The stuff, the techniques you should remember and take with you home, and which is the ones we use all the time in efficient algorithms, is this multi-way merging and splitting, distribution sweeping, multi-way trees, sometimes with buffers on them. You can put buffers on all kinds of trees and get new results. And then time-forward processing, like I just talked about. And I think that was what I wanted to say. Questions? I want to see if I'm online here. If I'm online, I want to show you something. Here. This is just to show you that it works in practice. So we have a startup that we started 3 years ago that does massive terrain computation, where we sell software and services and different stuff. And you can go and see more about it in Scargo. The main reason why I mention it is two. One is it works. I mean, we can actually sell software to people and services, so it works in practice. And another thing is, don't tell anybody, but everything we do is time-forward processing. So I think it's time for coffee now. Okay?